A few weeks ago, I had the opportunity to visit an engine manufacturing plant in Spain where I got to see something really interesting called bore spray coating, where a cylinder coating is basically directly sprayed onto an aluminum engine block instead of using a traditional cast iron cylinder sleeve or liner. This process apparently reduces engine weight and it improves efficiency and emissions, but it also makes the engine non-rebuildable. In response to this, a lot of viewers commented how this making engines non-rebuildable is actually planned obsolescence and how non-rebuildable engines are bad for the environment. And this got me thinking, and then I decided to dig into it, and then based on all of this thinking and digging, I made this video. And in this video, we're gonna do two things. Number one, we're going to list and explain all the different mass production popular engine cylinder coating processes, stuff like Nikasil, Alusil, and so on and so forth. There's a bunch of them. We're going to see how they work, how they're different from each other, why they came into existence, and what kind of benefits and drawbacks they offer. And this will then help us understand whether these coatings really are planned obsolescence disguised as environmental friendliness, or whether there's a different motivation for these coatings. And number two, what we're going to do is that I'm going to use data from scientific research and reports from reputable sources to try and hopefully quantify and measure the environmental impact of non-rebuildable engines. One of the first cylinder coatings to be used in mass production is also probably one of the most famous. It's called Nikasil. Nikasil stands for nickel silicon carbide, and it's essentially an electroplating process, and so it works just like any other electroplating process. So what we have is a solution or a bath, basically a liquid, which is filled with nickel ions and silicon carbide particles. Silicon carbide is essentially a ceramic which is extremely wear resistant. What we do is that we put our cylinder block in the bath, and then we connect the negative side of a power source to that block, which makes the block our cathode. And then we take a nickel bar, dip it in the solution, and connect the positive side of our power source to the nickel bar, which makes it our anode. When we turn on our power source, electricity of course starts flowing from the anode to the cathode. Nickel ions from the solution, they move toward the cylinder and coat its surface, whereas silicon carbide particles, they get trapped in the nickel layer, creating a very thin, but at the same time very hard and very wear-resistant Nikasil coating. Okay, so that's how it works, but we have to ask ourselves, why bother with all of this electroplating nonsense when there's really nothing wrong with traditional cast iron sleeves, because they've been used on thousands upon thousands of engines without really any sort of major widespread issue? Well, what's important to understand when it comes to cylinder coatings is that they were never about fixing a problem. They were always about pushing the limits, enabling the engine to do something that it could not do before. In other words, cast iron sleeves, they have some key limitations that Nikasil, for example, does not. Number one, Nikasil is anywhere between 0.05 to 0.15 millimeters thick, whereas a cast iron sleeve is anywhere between 2 to 7 millimeters thick. And that means that a cast iron sleeve is essentially a barrier to heat transfer, because cast iron is a lot worse at heat transfer and heat dissipation compared to aluminum. The much thinner Nikasil coating is better at heat dissipation and heat transfer. And because we have that, we can push our engine into higher combustion pressures and higher combustion temperatures without overheating or straining the engine, and that means more performance. Nikasil coatings also have much better dimensional stability under any conditions compared to a cast iron liner. And this improved dimensional stability means that we can make giant bore engines and reduced bore spacing. We also, for example, we can make two-stroke cylinders with giant ports. All of this was impossible and is still impossible with a cast iron sleeve because we compromise the structural integrity of the sleeve. And that's because a cast iron sleeve, it creates strength with bulk. It must have a certain amount of material everywhere to remain stable. the fact that the cast iron sleeve expands and contracts when heating up and cooling down at a different rate compared to the surrounding aluminum block, and so it can sink or seize in the block or crack or whatever, this is another aggravating circumstance for the sleeve. Number 3, a Nikasil coating is actually much more wear resistant and durable compared to a cast iron sleeve, and that means that it deals better with high loads and extreme piston speeds, and that of course means a higher redline and potential for even more performance. The increased durability and wear resistance also of course means that the engine itself lasts longer with a Nikasil coating. Number 4, a Nikasil coating offers reduced friction compared to a iron sleeve, and reduced friction of course improves efficiency and performance. And finally, number 5, a Nikasil coating is much thinner, there's much less material, so we're actually saving weight, usually about 5 to 7% per engine block. That's how much weight we're saving, and weight reduction is always a good thing, as we know, because it improves both performance and fuel economy. As you can see, Nikasil is better at everything that matters compared to a traditional cast iron sleeve. Now, Nikasil was actually perfected in the late 60s by Mahle, German company which was working at the time together with NSU, and they were trying to make a Wankel engine apex seals of the rotor last a reasonable amount of time in rotary engine casings, aluminum casings or housings. The first to actually implement Nikasil in a piston engine was Porsche, that's how you say it. They first used it in their 917 race car, and then later in their 911 RS. After this, Nikasil started spreading quickly to motorcycles, where it became very popular in two-stroke motorcycles, where it's used successfully to this day. And then in the 90s, we also got it in BMW M52 inline 6, the M60 V8, and in Jaguar's AJ V8 engine. However, it was soon discovered that Nikasil had a weakness. It was weak to high sulfur fuel, low quality, high sulfur content fuel. The most common explanation of the problem is that the sulfur in the fuel reacted with moisture to create sulfuric acid, which essentially over time dissolved the Nikasil coating. And without the Nikasil coating, aluminum has the wear resistance of a wet biscuit, and so the engine fails. This was really only a problem in United States back at the time, not really so much in Europe, almost in some countries absolutely not a problem, because already in Europe at the time in the 90s we had fuel quality standards which limited the amount of sulfur in the fuel. However, this fuel quality weakness wasn't really what spelled doom for Nikasil. What spelled doom for it was that it's a slow, labor-intensive process, and that makes it expensive. And that is the number one word on the list of words that manufacturers hate. So what manufacturers decided to do is to try and get all the beautiful benefits of Nikasil without paying all the money. And so they moved some orders around and created Alusil. Alusil is essentially an etching process. You cast the entire engine block with a very high content of silicon, usually around 17%. Once the block is cast, you either chemically or mechanically etch away the aluminum in the cylinder, and so what remains exposed is a layer of silicon. And silicon is a durable and hard-wearing material. Overall, the process is much faster and more cost-effective than the electroplating complexities of Nikasil. But still, manufacturers were not happy. They wanted to make it even cheaper. And so what they did is that they came up with another acronym. This one was called Lokasil. And the whole point of Lokasil is to not cast the entire engine block with a high content of silicon, because you really only need the silicon in the cylinders, right? So what Lokasil does is that it uses pre-made inserts, which are essentially silicon suspended in some sort of resin. These pre-made inserts are placed in the mold, and then the melted aluminum enters the mold. The high-temperature aluminum melts away the resin, and so what remains is a layer of silicon on the surface of the cylinder, the only place where you actually need it. Now manufacturers were finally happy because Lokasil was ultra-fast and dirt cheap. a most arousing combination of words for any manufacturer. And what one manufacturer likes, so too does another. But what manufacturers do not like is paying license fees to other manufacturers. So what do? Of course, they come up with more acronyms. Our final acronym for today is called Silitec. Now, Silitec is very similar to Lokasil because you also have a pre-formed liner and then you cast the block around that liner, but apparently it's legally different enough. The liner is of a different composition enough, and maybe the manufacturing is slightly different, so you don't have to pay license fees. In fact, so Mercedes doesn't have to pay license fees because you can sort of think of Silitec as Mercedes' version of Lokasil, because Silitec is almost exclusively used on Mercedes engines. All three of these coatings, Alusil, Lokasil, and Silitec, they were supposed to offer the benefits of Nikasil while having a much lower cost for manufacturers. In other words, they were supposed to last longer and be more durable than a traditional cast iron liner, just like Nikasil is more durable than a cast iron liner. Unfortunately, in practice, Lokasil, Alusil, and Silitec, they proved to be less durable. They lasted less than a traditional cast iron liner. The issue is that over time, the exposed silicon particles, they broke away. They fell off from the cylinder. They circulated through the engine. The bores were left exposed. We got bore scoring, loss of compression, high oil consumption, and eventually a failed engine that needs a rebuild. Lokasil was sort of the worst one of all. It had the poorest longevity. Fortunately, it was the one with the least widespread use by far. Silitec sort of did okay in naturally aspirated applications, did worse in high-temperature direct injection turbocharged applications. Alusil, also a very mixed track record, was absolutely horrible in some cases, sort of okay in others. Overall, we can conclude that Alusil, Silitec, and Lokasil, from a long-term reliability perspective, they were not a success. Interestingly, with the exception of the Chevrolet Vega, or is it Vega? Viva Las Vegas. So it's a Vega. Chevrolet Vega. With the exception of that car, it was pretty much exclusively German manufacturers that used Lokasil, Alusil, and Silitec, and more often in their more upmarket, more expensive engines, large V8, V12. Yeah, just saying. Now, despite the sort of reliability failure of these coatings, it is undeniable that a thin coating has many benefits over a thick iron liner. And so manufacturers did not give up. They decided to try to find a new way to avoid cast iron liners, and what they did ultimately and finally is that they gave up on all the etching and the scratching, and they decided to spray the cylinder liner onto the block. And that is the exact process that I got to see when I visited the Horse Valladolid factory in Spain. It is called bore spray coating. Now, there are different kinds of these processes, but they all fall within the same category, within the same sort of family of cylinder coatings, and they can be called thermal spray coatings. All of these processes have in common the fact that we have either one wire or two wires made from whatever metal or combination of metals we want. Usually it's a nickel-iron alloy or something similar. You can think of these two wires as essentially welding wires. We pass a ridiculous amount of electricity through these wires. The electricity arcs from one wire to the other, just like a spark plug, but much more intense. This arc is essentially plasma. It's a superheated gas, a high-energy state of matter. This incredibly hot gas then starts melting and atomizing the wire into tiny droplets. When that starts happening, we use another gas, either compressed air or nitrogen, to push, carry, and deposit these droplets of molten metal onto the cylinder. The droplets splatter, instantly transfer heat away, and solidify on the cylinder as a special coating. Now, thermal spray coating requires a massive initial investment in very expensive machinery, but in the long run and at sufficiently high volumes, it's actually more cost-effective per cylinder than a iron liner. The added benefit for manufacturers is that the process is generally very fast, easily scalable, and it's easy to adapt it from one engine configuration to another because the very same machine can do all kinds of different engine blocks with minimal downtime in between. The end result is again, of course, a very thin coating, which is supposed to improve heat transfer, reduce friction, and improve durability. Two engines which have thermal spray coatings, which will be well known to petrol heads, are the Ford Coyote 5-liter V8 and the VR38 DETT engine as found in the R35 and Nissan GTR. Of course, there are nowadays many more engines with thermal spray coatings on them, and overall in the last decade or so, thermal spray coatings have demonstrated to overall have a noticeably better long-term reliability track record when compared to Alusil, Silitec, and Lokasil. Okay, so now we know how it's done, we know the benefits, and that means it's time to ask the next question, and that is planned obsolescence. Is making engines non-rebuildable through the use of engine coatings planned obsolescence? Before we answer that, something very important that has to be said. Coatings do not necessarily make an engine non-rebuildable. In the case of Nikasil, an engine is rebuildable. There are many businesses around the world which do replating of engines with Nikasil. In the case of Alusil, Lokasil, and Silitec, we can say that the engine is non-rebuildable because you would theoretically need to cast the engine again. There are some companies and businesses around the world which rebuild Alusil, Silitec, Lokasil engines. Probably an even lower number of companies that do this rebuild well because you have to re-sleeve the engine. You cannot recoat it, you cannot replate it. You can convert such an engine to Nikasil, but you cannot make it Alusil again. So the only thing you can do is to either make it Nikasil or put in sleeves, and doing the sleeve way can be tricky. So, hard to rebuild is all we're going to say about Lokasil, Silitec, and Alusil. Thermal spray coating, there is nothing stopping, in theory, anyone from taking a worn-out thermal spray coating engine, machining away the old coating, and then reapplying the coating again and having essentially a rebuilt engine. You do the honing and it's rebuilt. Actually, there is something stopping someone from doing that, and it's the cost. The thermal spray coating machinery and optical verification machinery that's needed for it is so prohibitively expensive that your nearest machine shop has no chance of affording it. So, the engines are not non-rebuildable. It's the machinery that is expensive. So, let us rephrase the question. Is making engines non-rebuildable through the use of prohibitively expensive equipment just another form of planned obsolescence? The answer is no. And it's no because our question contains in it the answer: prohibitively expensive equipment. Think about it. To achieve thermal spray coatings, you have to do a lot of research and development. Then you have to invest in extremely expensive machinery that applies the coating, and then an extremely expensive machinery to do the optical verification of whether the coating has been applied properly and to have the necessary quality control. Doing this would be probably the stupidest way of achieving planned obsolescence because it's extremely expensive. And planned obsolescence can be achieved in basically free, extremely cheap, very easy and inconspicuous ways. You take your part, whatever it is, you use a simulation software, you simulate a certain number of thermal cycles. And then you take whatever part you want, water jacket, oil gallery, cylinder, support, structure, doesn't really matter. And you reduce the thickness of that part, or you switch it to a ever lower quality of material until you achieve failure in your simulation at the desired number of thermal cycles. That's it. That's planned obsolescence. It costs you nothing. It's actually saving you money because you're using less or a cheaper material. The deal is that with modern emissions and efficiency standards, manufacturers are using aluminum engine blocks and coatings not because they want to, but because they have to. Modern engines are expected to make maximum power and minimal emissions. That is extremely hard to do, and it leads to pretty much always to very high combustion pressures, very high temperatures, and the engine tends to run very hot. So an open deck aluminum engine block with a very thin cylinder coating is needed for thermal control of such an engine. Without this configuration, the engine would melt down. Now, you might be tempted to say, hey, but the Toyota 2JZ can make 1000 horsepower reliably without melting down, and that's a cast iron block. Sure, and it's also a very irrelevant example because that's a racing project car somebody built, and to not melt down, such engines, and in motorsport as well, they run at 11:1 air-fuel ratio, something like that, and that is extremely rich. The extra fuel in the air-fuel mixture vaporizes and it takes away heat temperature from the combustion chamber and prevents knock and engine, failure. A production engine cannot, especially a modern one, cannot afford to ever run at such a high air-fuel ratio because that leads to, number one, horrible emissions, and number two, horrible fuel economy. So modern engines, they have to make a lot of horsepower per liter of displacement while at the same time running lean. And again, as we said, the result is always going to be very high temperatures, and we need to control these temperatures somehow. It also explains the Nissan R35 VR38 DETT engine. The Nissan R35 had to make more power than the Nissan R34 while respecting more stringent emission standards. This is why the R35 had to abandon the cast iron RB26 engine block and go for an aluminum-coated engine block. Now, you may think that the R35 is not a relevant example for anything, right? That's extreme performance, and we're kind of talking about family car engines here. They have much lower ambitions. Well, here's an example. When I was in the Horse Valladolid engine factory in Spain, I had the opportunity to see the HR13 engine, which is a 1.3-liter four-cylinder which makes 170 horsepower in certain markets. When you take the horsepower per liter of that engine, it's right around 130 horsepower per liter, just like the Nissan R35 at 500 horsepower during its, early years. So what was extreme performance a decade ago is what we expect from family car engines today. And now the final question, are non-rebuildable engines bad for the environment? I'm going to answer that question by throwing a lot of numbers at you. These numbers come from multiple sources. If you want to see the sources, they're down in the description. And I decided to focus on just the European Union and only on CO2 emissions to keep it manageable for a single person. Okay, let's see the numbers. In 2023, 10.5 million new cars were registered in the EU. The average European drives 10,900 kilometers per year. The average fuel economy for these new passenger cars is 5.6 liters per 100 kilometers. The average CO2 emissions are 106.4 grams of CO2 per kilometer. Thermal coatings improve engine efficiency by 5% and thus reduce CO2 emissions by 6.5 grams per kilometer. And if every one of our 10.5 million cars gets a thermal spray-coated engine, then we are going to reduce our CO2 emissions by 41,669 tons of CO2 per year. Now, let's imagine that our 10.5 million cars are at the end of their lifespan. Each of them has an engine block. The average weight of an engine block in Europe is 30 kilograms. Recycling 1 ton of aluminum produces 0.7 tons of CO2 emissions. So if we recycle all of our 10.5 million engine blocks, we'll produce 220,500 tons of CO2. Now, engine remanufacturing produces 20% less CO2 emissions than aluminum recycling per ton. So if we rebuild all of our engines instead of recycling them, then we will save 44,100 tons of CO2. However, thermal spray coating saves 41,669 tons of CO2 per year, and it takes a car a decade or two to reach the end of its service life, which means that overall, thermal spray coating saves much more CO2 than rebuilding does. Even if we take our 5% efficiency gain from thermal spray coating to be over-optimistic, we halve it, we put it to 2.5%, even in that case, thermal spray coating still saves more CO2 than rebuilding. So thermal spray coatings are good for the environment. Well, maybe. Let's be realistic. What I just told you is superficial data analysis at best. It's an educated guess at its most optimistic version because there is an incredible number of data and an incredible number of variables we're talking about here. And I'm just analyzing a little part of it from the data that is publicly available. So let me just point out some of the issues. We're comparing rebuilding versus recycling. The reality is, of course, that not all the raw materials for engines come from recycled metals, of course. And this varies across different engines, different parts of the world, different manufacturers. And that's, of course, because the products of recycling simply aren't suitable for certain engine types or manufacturing processes. And recycling itself is also a process of great variation. It produces stuff of different grades of qualities. And for the recycling, it depends where your energy comes from. Is it renewable, And engines themselves, recycling them can also be tricky and complicated because you have your coatings, you have your hardenings on the materials, you have weird alloys, you name it. All of that can be very tricky to recycle. And we're just taking into account CO2. There's a bunch of other stuff in both rebuilding and recycling. You have your chemicals, your residues, your other emissions, and any one of those could skew the results in a different direction. And what we're also not taking into account is that when you rebuild an engine, you're reviving something that has the emission standards from 10, 20 years ago. And nowadays, engines can improve a lot in 10 or 20 years. So what I'm really trying to say is that there is an incredible amount of data here, an incredible amount of variables, and trying to sort of give you this one simple sentence, this is good, this is bad, I don't think that's realistic or scientific or objective. So what I can give you is my subjective personal opinion that I have sort of developed after reading and digging through all of these papers and reports and research. And I personally think, based on the publicly available data, that thermal spray coatings, when applied properly and when they do not shorten the life of the engine, like Alusil, Lokasil, and Silitec, they are better for the environment than engine rebuilding, because engine rebuilding cannot hope to offset the amount of CO2 that is saved by the thermal spray coatings, even if we are pessimistic about their efficiency gains. And we also have to be realistic here. The cost of engine rebuilding has risen so much in most developed countries that it simply doesn't make financial sense to do a proper rebuild of a family car engine that is 10 or 20 years old. At that stage, the rebuild of the engine is usually going to cost more than the car itself. Realistically, the only engines that get rebuilt nowadays are industrial, freight, or vintage, special, valuable motorsport, or a combination of thereof. So, engine cylinder coatings. How they work and what they do, both for your engine and for the environment. I hope you enjoy that. I hope you maybe learned something. And as always, thanks a lot for watching. I'll be seeing you soon with more fun and useful stuff on the Day4A channel.